Section 1 Introduction. We're here to discuss a persistent issue in reinforcement learning, RL, which is the creation of reward functions that efficiently guide an agent towards desired behaviors. This process, known as reward shaping, has traditionally been done by manually designing rewards based on expert intuition and heuristics. However, this method is time-consuming, requires expertise, and may not always yield the best results. Inverse reinforcement learning, IRL, and preference learning have been proposed as potential solutions to reward shaping. These methods involve learning a reward model from human demonstrations or preference-based feedback. However, they still require significant human effort or data collection. Moreover, the reward models based on neural networks are not easily interpretable and cannot be generalized beyond the domains of the training data. In this paper, we introduce a new framework, Text2Reward, which generates dense reward code based on goal descriptions. For example, if the RL goal is to push the chair to the marked position, Text2Reward generates dense reward code using large language models, LLMs, based on a compact, Pythonic representation of the environment. This dense reward code is then used by an RL algorithm such as PPO and SAC to train a policy. Unlike inverse RL, Text2Reward does not require data and generates symbolic rewards that are highly interpretable. It also differs from recent work that used LLMs to write sparse reward code, i.e., the reward is non-zero only when the episode ends, with hand-designed APIs. Our free-form dense reward code can handle a wider range of tasks and can utilize established coding packages, e.g., NumPy operations over point clouds and agent positions. However, due to the sensitivity of RL training and the ambiguity of language, the RL policy may not always achieve the goal or may achieve it in unintended ways. To address this, Text2Reward executes the learned policy in the environment, requests human feedback, and refines the reward accordingly. We tested Text2Reward on 2 robotics manipulation benchmarks, Mani Skill 2, MetaWorld, and 2 locomotion environments of MuJo-Co. In 13 out of 17 manipulation tasks, policies trained with our generated reward code performed as well or better than those trained with reward code carefully tuned by human experts. For locomotion, Text2Reward learned 6 novel locomotion behaviors with over 94% success rate. We also demonstrated that the policy trained in the simulator can be deployed on a real Franca Panda robot. With human feedback of less than 3 iterations, our method can iteratively improve the success rate of learned policy from 0 to almost 100%, as well as resolve task ambiguity. In summary, our experiments showed that Text2Reward can generate generalizable and interpretable dense reward code, enabling a wide range of RL tasks and a human-in-the-loop pipeline. We hope that these results will inspire further research in the intersection of reinforcement learning and code generation. Now, let's delve into the Text2Reward framework for reward shaping. Text2Reward takes a goal instruction and a description of the environment as input and generates a dense reward function to be used by any RL algorithm. In RL, the aim is to learn a policy that maximizes the expected reward in an episode. To train a policy to achieve a goal, the key is to design a reward function that specifies the goal. The reward function can take various forms such as a neural network or a piece of reward code. In this paper, we focus on the reward code given its interpretability. In this case, the observation and the action are represented as variables, such that the reward does not need to handle perception. It only reasons about abstract variables and APIs in code. Reinforcement learning from task completion rewards is difficult because the reward signals are sparse and delayed. A dense reward function is useful since it encourages key intermediate steps and regularization that help achieve the goal. In the form of code, the dense reward function returns a scalar value at each time step, instead of only at the final time step. In this part, we describe the core of Text2Reward for zero-shot and few-shot dense reward generation. The instruction is a natural language sentence that describes what we want the agent to achieve, e.g., push the chair to the marked position. It can be provided by the user, or it can be one of the subgoals for a long horizon task, planned by the LLM. To ground reward generation in an environment, it is necessary for the model to know how object states are represented in the environment, such as the configuration of robots and objects, and what functions can be called. We adopt a compact representation in Pythonic style, which utilizes Python class, typing, and comment. This Pythonic representation is prevalent in LLM's pre-training data, making it easier for the LLM to understand the environment. Section Summary. The paper introduces Text2Reward, a framework for generating dense reward code based on goal descriptions in reinforcement learning, RL. Unlike traditional methods that rely on manual reward design or data collection, Text2Reward generates symbolic reward code using large language models, which is interpretable and can be applied to a wide range of tasks. The framework also incorporates human feedback to refine the reward and improve the success rate of the RL policy. Experimental results demonstrate that Text2Reward achieves comparable or better performance than expert-tuned reward code in manipulation tasks and learns novel locomotion behaviors with high success rates. Section: Background Knowledge. We understand that creating dense reward codes for language learning models, LLMs, can be quite a task due to the lack of sufficient data. However, recent studies have shown that providing relevant function information and usage examples can make this process easier. Taking a cue from these studies, we offer functions that can be useful in this environment as background knowledge. For instance, we provide functions from NumPy, SciPy for calculating pairwise distance and quaternion, along with their input and output types and explanations in simple language. We also know that providing relevant examples as input can help LLMs solve tasks more efficiently. We assume that we have access to a pool of pairs of instructions and verified reward codes. Experts can start the library, and then it can be continually expanded by our generated dense reward code. We use a sentence embedding model to encode each instruction. When we get a new instruction, we use the embedding to find the top k similar instructions and combine the instruction code pairs as few-shot examples. Once the reward code is generated, we run the code in the code interpreter. This step can provide valuable feedback, such as syntax errors and runtime errors. We use this feedback to refine the LLM continuously. This iterative process helps correct errors systematically and continues until the code is error-free. Our experiments show that this step reduces error rates from 10% to almost zero. Humans often do not specify their exact intentions in a single interaction. The initial generated reward functions may be correct in theory but not optimal in practice. For example, when instructing a robot to open a cabinet, the user may not specify whether to pull the handle or the edge of the door. Both methods open the cabinet, but the former is preferable as it is less likely to damage the furniture and the robot. In another scenario, the initially generated reward function may be too difficult to achieve. For example, telling a robot to clean up the desk is more challenging than instructing the robot to pick up items on the desk and then put them in the drawer below. Both instructions have the same intent, but the latter provides intermediate objectives that simplify the learning problem. To solve the problem of underspecified instructions leading to suboptimal reward functions, our system, Text2Reward, actively seeks human feedback to improve the generated reward functions. After every reinforcement learning (RL) training cycle, users are shown videos of task execution by the current policy. Users then provide valuable insights and feedback based on the video, pointing out areas for improvement or errors. This feedback is incorporated into subsequent prompts to generate more refined and efficient reward functions. We test Text2Reward on manipulation and locomotion tasks across 3 environments: MetaWorld, MoniSkill2, and Jim-Mu-Jo-Co. We use GPT-4 as the LLM. We select the RL algorithm, PPO or SAC, and set default hyperparameters based on the performance of human-written reward, and keep that constant in all experiments on this task for RL training. We demonstrate manipulation on MetaWorld, a commonly used benchmark for multitask robotics learning and preference-based reinforcement learning, and MoniSkill2, a platform showcasing a diverse range of object manipulation tasks executed within environments with realistic physical simulations. We evaluate a variety of manipulation tasks including pick and place, assembly, articulated object manipulation with revolute or sliding joint, and mobile manipulation. For all tasks, we compare Text2Reward with Oracle reward functions tuned by human experts. For locomotion tasks, we demonstrate our method using Jim-Mu-Jo-Co. Due to the lack of expert-written reward functions for locomotion tasks, we evaluate the policy based on human judgment of the rollout video. We develop 6 new tasks in total for 2 different locomotion agents: Hopper, a 2D uni-pedal robot, and Ant, a 3D quadruped robot. The tasks include move forward, front flip and back flip for Hopper, as well as move forward, lie down, and wave leg for Ant. Section Summary. Generating dense reward codes for language model-based reinforcement learning, LLM, can be challenging due to data scarcity. To address this, we provide relevant function information and usage examples as background knowledge, utilize few-shot examples to assist code generation, and reduce errors through code execution feedback. Additionally, we improve reward codes by actively requesting human feedback, integrating critical insights and suggestions into subsequent prompts to refine and optimize the generated reward functions. Our experiments demonstrate the effectiveness of these approaches in manipulation and locomotion tasks across different environments. Section 3.3 Real Robot Manipulation. We've developed a method that allows reinforcement learning, RL, agents, trained in a simulator, to be directly applied in the real world. This approach doesn't require the extensive parameter adjustments that model-based methods like Model Predictive Control, MPC, do. Instead, it only needs minor calibration and the addition of random noise to transition from the simulator to the real world. To demonstrate this, we conducted an experiment using a Franka Panda robot arm. We tested our approach on two tasks, picking up a cube and stacking a cube. To determine the state of the object for our RL policy, we used the segment Anything model, SAM, and a depth camera to estimate the position of objects. We asked SAM to segment each object in the scene, and combined this segmentation map with a depth map to create an incomplete point cloud. We then estimated the object's position based on this point cloud. We also conducted an experiment to see if human feedback could improve or correct the reward code, enabling RL algorithms to successfully train models in a given environment. We tested this on a task called Stack Cube, which involves reaching for a cube, grasping it, placing it on top of another cube, and releasing it while keeping it stationary. We sampled 3 generated codes from zero-shot and few-shot methods and performed this task with 2 rounds of feedback. We also conducted experiments on a locomotion task called Ant Lie Down, where the initial training results did not meet the user's preferences. The user providing the feedback only had access to the rollout video and learning curve, without any code. Our results show that our Text2Reward method performs comparably to expert-designed rewards on manipulation tasks. In fact, on 4 out of 17 tasks, Text2Reward even outperformed the human expert, either in terms of the speed of convergence or the success rate. This suggests that large language models, LLMs, have the potential to draft high-quality dense reward functions without any human intervention. Our method can also generate dense reward functions that generalize to novel locomotion tasks. We demonstrated this by training Text2Reward on a real robot, using the same 7 degrees of freedom Franka Panda robot arm as in the Mani Skill 2 simulation environment. Text2Reward can also resolve ambiguity from human feedback. For example, in one case, the instruction, control the ant to lie down, was ambiguous in terms of the ant's orientation. After observing the training result of this instruction, the user was able to provide feedback in natural language, and Text2Reward was able to regenerate the reward code and train a new policy that successfully catered to the user's intent. However, given the sensitivity of RL training, sometimes a single turn generation cannot generate good enough reward functions to complete the task. In these cases, Text2Reward asks for human feedback on the failure mode and tries to improve the dense reward. We demonstrated this on the Stack Cube task, where zero-shot and few-shot generation in a single turn failed to solve the task stably. For few-shot generation, we found that interactive code generation with human feedback can improve the success rate from 0 to 1, as well as speed up the convergence speed of training. However, this improvement is dependent on the quality of the reward function generated in the beginning. For relatively low-quality reward functions, the improvement in success rate after iterations of feedback is not as pronounced. This problem may be solved in a sparse to dense reward function generation manner, which generates the stage reward first and then generates reward terms interactively. We leave this paradigm for possible future work. Section Summary. The authors demonstrate that their RL agents, trained in a simulator, can be directly deployed in the real world with only minor calibration and the introduction of random noise for sim to real transfer. They also show that their Text2Reward method can generate dense reward functions for robotics manipulation and locomotion tasks that achieve comparable results to expert-designed rewards, and even outperform human oracle in some cases. Additionally, Text2Reward can resolve ambiguity from human feedback and improve RL training through interactive code generation. Section 4.2 Error Analysis on Generated Function. We've carried out an analysis of the errors that occur in the reward functions we generate. We manually reviewed 100 examples of these functions, each one created by either zero-shot or few-shot prompting across 10 different tasks in the Mani Skill 2 set. Each task had 10 unique reward codes. These functions were specifically generated for our error analysis and didn't provide any feedback to the large language models, LLMs. We identified 4 types of errors. 1. Misuse of class attributes. 2. Invention of non-existent attributes. 3. Errors in syntax or structure. 4. Use of the wrong package. Our analysis showed that the overall error rate was about 10%. Of these errors, 30% were due to syntax or structure issues, while the rest were caused by difficulties in selecting the correct function and attributes from the available options. This suggests that there's room for improvement in understanding how to choose the right function and attributes, especially for the code generation community. Reward shaping is a significant challenge in reinforcement learning, RL. Traditionally, we've used handcrafted reward functions, but creating these is a time-consuming process that requires expertise. Inverse reinforcement learning, IRL, offers a potential solution by recovering a nonlinear reward model from expert trajectories to aid RL learning. However, this method requires a large amount of high-quality trajectory data, which can be hard to come by for complex and rare tasks. Another approach is preference learning, which builds a reward model based on human preferences. In this method, humans distinguish preferences between pairs of actions, and a reward model is built using this preference data. However, this method still requires some human annotated preference data, which can be expensive or difficult to collect in some cases. Both of these common approaches to reward shaping require a lot of high-quality data, which can limit their generalizability and efficiency. In contrast, Text2Reward works well with limited, or even no, data input and can be easily generalized to new tasks in the environment. Large language models, LLMs, have shown impressive reasoning and planning capabilities. Recent research has shown that the knowledge in LLMs can be useful for RL and can change the way we acquire policy networks based on data. This trend is leading to the rise of autonomous agents powered by LLMs, with an increasing number of methods using LLMs as policy networks during the RL process, indicating a promising direction in this field. Instead of directly using LLMs as the policy model or the reward model, Text2Reward generates dense reward code to train RL policies. This approach has the advantage of flexibility in the type of agent model and efficiency in inference. Using LLMs for embodied applications is becoming a popular research trend, with typical directions including planning and reasoning through language model generation. Recent research has used the capabilities of LLMs to assist in learning primitive tasks by fine-tuning LLMs on robotic trajectories to predict primitive actions. Unlike these methods, Text2Reward generates reward codes to learn smaller policy networks. A recent study combined sparse reward code and model predictive control, MPC, to synthesize robotic actions. Unlike this study, our work trains model-free RL agents that show greater adaptability.